Welcome to our presentation on quantum black holes and gauge gravity duality. Today, we will delve into the fascinating relationship between quantum black holes and gauge gravity duality. Our objective is to understand information preservation and retrieval in black hole evaporation and to resolve the black hole information paradox. This paradox questions how information that falls into a black hole can be reconciled with the principles of quantum mechanics when the black hole evaporates due to Hawking radiation. This presentation is based on various seminal works, including those by Almheiri et al. And Penington. The primary goal is to explore the entropy of bulk quantum fields and entanglement in black holes. Understanding this relationship is crucial for addressing the black hole information paradox, a fundamental problem in theoretical physics. The paradox arises because classical general relativity suggests that information is lost when black holes evaporate, conflicting with the principles of quantum mechanics, which state that information must be conserved. Let's begin with the basics of JT gravity, which stands for Jacques-Teitelbaum gravity. This is a two-dimensional theory of gravity that simplifies the complex problem of quantum gravity while retaining essential features. The action for JT gravity is given by equation 1. For an eternal black hole, the metric and dilaton are described by equation 2. This describes a black hole with constant negative curvature, which means the spacetime is curved in such a way that it can be represented by the hyperbolic plane. The Hawking temperature T0 is a characteristic temperature associated with the black hole's radiation. This setup provides a simplified yet powerful framework to study black hole thermodynamics and quantum effects. Next, we consider the scenario of an evaporating black hole. When a black hole is coupled to a heat bath, a shock of positive energy enters the black hole. This interaction leads to changes in the black hole's energy and temperature. The energy change due to this shock is described by equation 3. This equation illustrates how the black hole's energy and temperature are modified by external influences, such as the infalling matter from the heat bath. An evaporating black hole gradually loses mass and energy over time due to Hawking radiation. This process significantly alters the black hole's properties, including its temperature and entropy, and is a key element in studying the black hole information paradox. Quantum corrections play a significant role in the dynamics of black holes. These corrections modify the stress-energy tensor, which describes the distribution and flow of energy and momentum in spacetime. They also affect the dilaton field equations, leading to changes in the black hole's entropy and horizon dynamics. Gravitational backreaction is another critical factor. It refers to the response of spacetime to the presence of energy. As energy enters or leaves the black hole, the surrounding spacetime geometry adjusts accordingly. This backreaction influences the evolution of the black hole and the structure of spacetime around it. Together, quantum corrections and gravitational backreaction provide a more complete and nuanced understanding of black hole dynamics. They highlight how quantum effects can lead to significant modifications in classical descriptions of black holes. To understand the dynamics of black holes, it's crucial to consider their initial state preparation. The Hartle-Hawking state of ADS2 is prepared via a Euclidean path integral on the half-line. This state is significant because it provides a well-defined starting point for studying black hole thermodynamics and quantum effects. The state of ADS2 in the heat bath is given by the standard CFT Hamiltonian on the line, with times identified in such a way that the state in the right half-line is a descendant of the half-line vacuum with some complicated boundary conditions. In quantum mechanical terms, this state is mapped to the half-space vacuum by means of a diffeomorphism. The ADS2 region is dual to a conformal quantum mechanics at the boundary, making it natural to map the entire ADS2 region to a single point, while the bath is mapped to the rest of the half interval. This setup helps in understanding the initial conditions for black hole formation and evolution. Let's compare the eternal black hole with the evaporating black hole. An eternal black hole maintains a steady state with constant entropy and temperature. The initial state is described by the thermofield double, a maximally entangled state that provides a stable configuration. In contrast, an evaporating black hole experiences a dynamic process of mass and temperature change, leading to variations in entropy and the appearance of quantum extremal surfaces, or islands, that adjust the entanglement structure. The initial state is the Hawking-Hartle state, which includes complicated boundary conditions reflecting the interactions with the surrounding environment. Understanding these differences helps in exploring the varied behaviors of black holes and their implications for quantum information theory. The information loss paradox is the statement that the von Neumann entropy exceeds the Bekenstein-Hawking entropy. For an evaporating black hole, this paradox is solved by means of the concepts of generalized von Neumann entropy, quantum extremal surfaces, island rule, and replica wormhole. The resolution consists in a unitary page curve, which rises at early times, trivial quantum extremal surface, reaches a maximum equal to the Bekenstein-Hawking entropy, and then starts to decrease at late times, a non-trivial quantum extremal surface associated with an island, until it vanishes. A phase transition between the two types of quantum extremal surfaces occur at the page time. The island rule is associated with a replica wormhole in which the various replicas, copies, of the black hole in the Euclidean theory are connected, thus making the entropy small. As it turns out, there is a version of the paradox in the eternal black hole in which the calculation simplifies since there is no gravitational backreaction. In particular, the calculation of the contribution of the island becomes much more explicit in this case. The page curve in this context will stabilize at late times at a constant value equals to twice the Bekenstein-Hawking entropy of the two boundaries. In this context, we have really two black holes connected by a wormhole, which are maximally entangled in a thermofield double state. Now let's compare two types of entropy, von Neumann entropy and Bekenstein-Hawking entropy. The von Neumann entropy SVN is defined by equation 4. The von Neumann entropy measures the quantum information content of a system. It is a fine-grained entropy, capturing detailed information about the microstates of the system. In a closed quantum system, von Neumann entropy remains constant under unitary evolution, highlighting the preservation of quantum information. This property is fundamental in quantum mechanics, where the evolution of an isolated system is described by a unitary operator, ensuring that information is preserved. In contrast, the Bekenstein-Hawking entropy SBH is given by equation 5. The Bekenstein-Hawking entropy is a coarse-grained entropy, representing the macroscopic thermodynamic properties of the black hole. It is directly proportional to the area of the black hole horizon, reflecting the holographic principle, which suggests that the information content of a volume of space can be represented as a theory on the boundary of that volume. This principle is a cornerstone of modern theoretical physics, bridging the gap between quantum mechanics and gravity. In summary, the von Neumann entropy is key to understanding the information paradox, as it tracks the fine-grained information potentially lost in black hole evaporation, whereas the Bekenstein-Hawking entropy is central to the paradox due to its increase with horizon area and its apparent conflict with unitary quantum mechanics during black hole evaporation. The generalized entanglement entropy combines the fine-grained von Neumann entropy with the coarse-grained Bekenstein-Hawking entropy. This concept is crucial for understanding black hole dynamics in a quantum framework. The generalized entropy for the evaporating ADS2 black hole is given by equation 6. The so-called quantum extremal surfaces are found by extremizing the generalized entropy over the point x plus x minus, as described by equation 7. These surfaces are minimized in the spatial direction but maximized in the temporal direction, which is the reason why they are extrema of the entropy. The study of these surfaces helps in understanding how information is distributed within the black hole and how it changes over time. The behavior of black hole entropy varies over time. At early times, the quantum extremal surface is close to the classical bifurcation surface of the original black hole horizon. During this period, the generalized entropy increases linearly with time, dominated by the von Neumann entropy of the conformal matter, as shown in equation 8. At late times, the quantum extremal surfaces are located inside the old horizon, as indicated in equation 9, leading to a decrease in generalized entropy. This behavior aligns with the Page curve, which describes the time evolution of black hole entropy. The late time behavior is dominated by the area term, as given in equation 10. This decrease in entropy is crucial for resolving the information paradox. The Page time marks a phase transition in the entanglement structure of the black hole, reflecting the balance between the radiation and the remaining black hole. The late-time quantum extremal surface, at the boundary proper time u, corresponds actually to the intersection with the horizon of the ingoing null geodesic, which was emitted from the boundary at the earlier time u minus THP, where THP is the scrambling time. The island conjecture posits that in an evaporating black hole, quantum extremal surfaces, or islands, form inside the black hole interior and contribute to the entanglement structure. According to this conjecture, the fine-grained von Neumann entropy of the radiation is given by the generalized entropy formula in equation 12, which involves, in addition to the radiation region very far from the black hole, a disconnected island inside the black hole. This ensures that the evolution of the black hole and its radiation is unitary, preserving information. The inclusion of islands means that parts of the black hole interior are included in the entanglement wedge of the radiation, ensuring that information about the initial quantum state is not lost, but encoded in the radiation. The formation of these islands is a key development in the understanding of black hole information retention and resolution of the paradox. The entropy of the radiation can be calculated correctly using this prescription. By using holography, the evaporation of a two-dimensional ADS2 black hole into a heat bath can be described by three different but equivalent systems. 2D gravity. This is given by a two-dimensional JT gravity interacting with a conformal field theory of gravity-matter interaction living in the left half-line. This theory is coupled to a two-dimensional conformal field theory living in the right half-line. Quantum mechanics. This is given by conformal quantum mechanics living on the boundary of ADS2 space, i.e., it is the holographic dual of ADS2 by means of the ADS2 CFT1 correspondence. This theory is coupled to a two-dimensional conformal field theory living in the right half-line. 3D gravity. This is given by the three-dimensional theory of gravity in ADS3 spacetime, with a dynamical boundary in the left half-line, but a fixed boundary in the right half-line. This is the dual gravity theory, which by means of ADS3 CFT2 correspondence is associated with the original two-dimensional gravity theory. This latter theory should now be viewed as a conformal field theory living on the boundary of ADS3, which is a dynamical space in this case, much like the Planck brane found in the RS models. In holographic theories, the entanglement entropy of a region is proportional to the area of the minimal surface in the bulk ADS space, as given by the Ryu-Takayanagi formula in equation 13. This formula provides a direct way to compute entanglement entropy in holographic theories, connecting bulk geometry to boundary quantum information. The entanglement wedge of the black hole at late time, as described by the black hole entropy in equation 14, is an interval extending from a point in the heat bath to the quantum extremal surface, whereas in the holographic theory, this entanglement wedge is the region bounded by this interval and a minimal area surface in the ADS3 bulk. At late times, the entanglement wedge of the radiation, as described by the radiation entropy in equation 15, is the union of an interval which extends to infinity in the bath and the interval corresponding to the island which is found deep inside the black hole beyond the quantum extremal surface. From the three-dimensional perspective, this union corresponds to a simply connected bulk region. The entanglement wedge of the radiation at late times includes, therefore, parts of the black hole interior, ensuring that the information about the initial quantum state is not lost, but encoded in the radiation. This connection between bulk and boundary theories exemplifies the holographic principle, where a lower dimensional theory on the boundary describes the higher dimensional bulk physics. The replica trick is a very powerful method used to compute the von Neumann entropy by calculating the partition function for n replicas of the system, as shown in equations 16 through 19. This method involves computing the trace of the nth power of the density matrix and then analytically continuing n to 1. Thus, it involves computation on a replicated geometry, which can be reduced to computation of correlation functions in an orbifold theory by imposing permutation symmetry between the replicas and introducing cosmic branes and twist operators to account for the induced conical singularities. We also insert twist operators at the endpoints of the intervals whose entropies are being calculated. The replica trick is used to show that the generalized entropy is nothing else but the effective action in the limit in which n approaches 1. More importantly, the replica trick was used to show the existence of new topologically non-trivial gravitational field configurations, called replica wormholes, which dominate the path integral. When the interior of the black hole is fully connected to the n replicas, we get replica wormholes, leading to the island rule. These replica wormholes are new gravitational saddles that appear when calculating the entropy of Hawking radiation in a gravitational setting, providing non-trivial contributions to the path integral. This method highlights the deep connections between quantum mechanics, gravity, and information theory, and is crucial for understanding how information is preserved in black hole evaporation. In conclusion, JT gravity, quantum extremal surfaces, and the island conjecture provide a robust framework for resolving the black hole information paradox. The distinctions between von Neumann entropy and Bekenstein-Hawking entropy are crucial for understanding information preservation in black hole dynamics. The replica trick is essential for computing entropy and understanding complex entanglement structures in quantum gravity. Thank you for joining this presentation on quantum black holes and gauge gravity duality. We hope this has provided valuable insights into the intricate and fascinating world of black hole physics. Your curiosity and engagement drive the pursuit of knowledge in this profound area of study. In the remainder of this video, a detailed account of the calculations underlying this problem is presented.